Detroit, Michigan, 1942. The city was a cacophony of steel, smoke and ambition. Outside, the streets hummed with car traffic, but inside the armoured factories, the real engines of war roared. Massive steel doors led to cavernous assembly halls, where the smell of welding flux, burning grease and oil-stained concrete hung in the air like a permanent fog. In these halls, tanks, the backbone of the US armoured forces, were forged with meticulous precision. The Allied war effort depended not only on strategy and soldiers, but on the tireless labour of thousands of civilians whose hands shaped the tools of victory. The factory floors were a testament to human endurance. Long rows of Sherman M4 tanks and experimental variants in various stages of assembly stretched from wall to wall. Each tank was an intricate puzzle. Chassis, turret, engine, suspension and armour plates all needed to align perfectly, each component welded, bolted or riveted into place. The sheer size of the operation was staggering. Conveyor belts moved massive armour plates into position, while overhead cranes swung turret assemblies into place with the precision of a surgeon. Men and women worked 12-hour shifts, sometimes longer, under the pressure of wartime production quotas. For the Allied forces, speed was paramount. In North Africa, US troops struggled against Rommel's Afrika Korps, often outgunned and outnumbered. Every delayed tank meant a missed opportunity, a lost flank, a soldier in peril. Yet despite the urgency, the conventional assembly methods were slow. Standard practice required weeks to complete a single tank from start to finish. Every weld, every rivet, and every alignment check consumed hours that the war could not afford. Supervisors, engineers, and line workers alike felt the tension, a palpable anxiety that threaded through the factory like a live wire. Among the thousands of hands shaping steel, one civilian stood out, not because of rank or authority, but because of his mind. Jack "Mac" Harrison, a 32-year-old machinist and engineer, moved through the factory with quiet observation. He wore no uniform, no medals, only a grease-stained coverall and a notebook tucked into his back pocket. Where others saw routine, he saw inefficiency. Where others saw lines of tanks inching forward, he saw opportunities for revolution. His eyes scanned the assembly process with relentless focus, tracing the motions of welders, riveters, and crane operators. Each repetitive movement was logged in his mind. A wasted minute here, a misaligned plate there, a bottleneck caused by sequential assembly when simultaneous work could be possible. Mac had grown up in the industrial neighbourhoods of Detroit, the son of a machinist and a schoolteacher. By the time he joined the tank assembly lines, he had already spent a decade mastering the intricacies of mechanical systems. He understood tolerances down to a fraction of a millimetre and could visualize an entire assembly sequence in his head. He wasn't a soldier, yet he understood that the tanks he helped build would determine the fate of men in deserts, jungles, and hedgerows across the globe. Every inefficiency was not just a lost minute, it was a lost life. The monotony of the factory floor could be crushing. Shift after shift, the work was exhausting. Welders' faces glistened with sweat under the heat of torches, while the rhythm of riveting guns pounded like a relentless drumbeat. Men hunched over engine blocks for hours, checking torque and alignment, their muscles aching and eyes strained from precision work. Supervisors paced the aisles, clipboard in hand, counting tanks, noting defects, pushing for speed without compromising quality. The psychological pressure was immense. Workers whispered about the toll, some fainted from exhaustion, others broke tools in frustration, yet everyone pressed on, driven by patriotism, necessity, or fear of failure. Even within this environment, Mac's mind was restless. He noticed patterns that others ignored. A turret often required repeated adjustments before it fit perfectly. Engine components were aligned sequentially, when simultaneous work on subcomponents could save hours. Welders frequently paused to reposition heavy armour plates, consuming valuable minutes. Riveting was performed in linear sequences, Yet multiple sections could be riveted at once with the right fixtures. The more he observed, the clearer it became. The factory was a marvel of human effort, but it was far from optimized. One grey morning, Mac paused by a partially assembled Sherman and traced the contours of its turret with his hand. The metal was cool and heavy, perfectly machined, yet the assembly sequence felt archaic, almost ritualistic. He jotted notes into his notebook, scribbles, sketches, measurements, ideas that seemed trivial but could, in theory, save hours of labour. He imagined modular subassemblies, pre-aligned jigs, synchronized work teams. The sketches were rough, almost childlike in their simplicity, but in the crucible of war, simplicity could become genius. Whispers circulated among the assembly line workers about Mac's obsession with efficiency. "He's crazy," some muttered as he crouched over a weld joint, measuring angles and jotting calculations. Others watched with curiosity, noting that his innovations might shave minutes off repetitive tasks. Supervisors were wary. A mistake in assembly could be catastrophic. Tanks failing in combat would reflect not just on the factory but on the lives of the soldiers depending on them. Yet the possibility of drastically increased output tantalized even the most skeptical. As the sun climbed overhead, casting shafts of light through grimy windows, Mac moved along the line, absorbing every detail. He watched how cranes lifted turrets, how riveters synchronized with welders, how final inspections slowed progress as imperfections were corrected. His mind churned with possibilities. If only he could design a way to pre-assemble components off the main line, to create modules that could be slotted together with precision, the assembly process could be shortened dramatically. The idea seemed audacious, even impossible. Yet every great innovation began with the impossible, and the war would not wait for conventional wisdom. By the end of the shift, the factory was a symphony of motion, sparks flying, belts humming, and human hands moving in synchronized chaos. Mac walked home under the dim streetlights, notebook in hand, plotting experiments, sketching jigs, imagining modular assemblies. He was a civilian, invisible to most, yet his mind was already at war. Inefficiency was the enemy he could fight, and every wasted minute in the factory was a battle lost. Somewhere in the deserts of North Africa or along the frozen roads of Europe, soldiers would wait for tanks that were slow to arrive. Mac vowed that he would change that, not with bullets or bombs, but with the clever use of steel, sweat, and ingenuity. Detroit slept uneasily, unaware of the revolution brewing inside its steel factories. For Mac, the night was alive with possibility. The war behind the factory gates had only just begun, and he had already spotted the cracks in the armour of industrial convention. The morning after his long walk home, Mac returned to the factory with a renewed sense of purpose. The hum of machinery greeted him like an old friend, but his eyes were no longer passive observers. They searched, calculated, and critiqued every motion, every weld, every sequence of labour. Over the weeks he had spent tracing tank components with careful measurement, he began to see a pattern in the chaos: redundancy. Multiple teams performed overlapping tasks. Cranes waited for welders. Turrets were aligned manually, then checked, then realigned. Minutes became hours, and hours became lost opportunities. Mac's first step was to transfer his mental sketches into formal blueprints. In a dim corner of the factory, away from the line supervisors, he spread his notebook across a wooden table and began drafting precise diagrams. He imagined pre-assembled modules, turrets, engine blocks, and suspension units that could be constructed independently before being slotted into the main chassis. Each module would be pre-aligned with precision jigs, reducing the need for repeated adjustments. Rivets and bolts would be installed in parallel, not sequentially, using newly designed fixtures. The idea was audacious. No one had dared attempt such a radical reconfiguration of wartime assembly lines. He sketched late into the night, the scratching of his pencil mingling with the distant echoes of factory machinery. Mac's apartment was cramped, the walls lined with oil-stained rags and spare parts he had scavenged from the plant. On a small wooden desk, the blueprints grew more intricate with each revision. Measurements down to fractions of an inch, tolerances calculated to ensure that once modules were joined, the tank would maintain structural integrity. He also designed small mechanical guides to hold armor plates in place, reducing human error and minimizing time lost to repositioning heavy steel components. By the end of the first week, he had a prototype plan ready. It was not yet tested, not yet proven, but it existed. The problem, of course, was acceptance. Supervisors valued order and adherence to standard procedures, especially in wartime. A misaligned turret or a poorly welded hull could mean catastrophic failure in combat, or worse, death for the soldiers depending on these machines. Yet Mac believed that the system itself, not the workers, was the enemy. He would need allies to convince management or demonstrate results before they could dismiss him as a dreamer. Mac started small. He enlisted 2 colleagues he trusted, Tom Reynolds, a veteran riveter with a precise hand and unmatched patience, and Sarah Callahan, a young engineer recently transferred from the automotive side of the plant. Tom was skeptical but curious. Sarah saw potential immediately. Together, they began experimenting with miniature modules using scrap steel and retired tank components. They built small jigs to test alignment and parallel assembly, using mock-ups to simulate the full production line. The experiments were meticulous. Every misfit or misaligned part was documented, adjusted, and refined. As days turned into weeks, word of Mac's activities spread quietly among the line workers. Whispers filled the air. "That mechanic's at it again," some said. "Crazy, if you ask me," muttered others. Yet curiosity outweighed skepticism. A few volunteers joined after work hours, fascinated by the possibility of shaving precious hours off the grueling assembly schedule. In a factory dominated by routine and repetition, Mac's experiments introduced an unfamiliar excitement, a sense that change, even radical change, was possible. Meanwhile, supervisors began noticing his extended absences from the assembly line. Mac was careful, working mostly in corners, avoiding interference with critical production quotas. But one morning, Charles Whitaker, a senior production manager, approached him. Whitaker was a stern man in his 50s who had overseen tank production since the earliest M4 models rolled out of the plant. "Harrison," he said, his voice firm but not unkind, "what exactly are you doing here?" "We have quotas to meet. Every minute you're away, that's a tank delayed." Mac stood tall, grease-stained hands gripping his notebook. "Sir," he replied cautiously, "I think there's a way to reduce assembly time significantly. We can pre-assemble modules, align them with precision jigs, and install them in parallel. If successful, we could cut tank build time by as much as 70 to 80%. Whitaker's brow furrowed. He had heard promises like this before, dreams from engineers and mechanics who didn't understand the practical realities of mass production. Yet there was something in Mac's calm confidence, the methodical notes and diagrams in his hands, that made him pause. 70 to 80%? Whitaker echoed, skepticism heavy in his tone. "That's impossible. No one has ever achieved anything close on a Sherman line. Our men in North Africa need tanks, not experiments." Mac nodded. He understood the risk. "I'm not asking to halt production. I'm asking for a small test, a single hull, a single turret, assembled using these methods. If it works, we can scale. If it fails, we've lost nothing but time in the test." Whitaker studied him, the factory floor stretching behind them, a sea of sweat-streaked faces and moving steel. Finally, he gave a measured nod. "All right, Harrison. One test, no more. If it fails, you stay on the line like the rest." The trio set to work immediately. They selected a recently started M4 hull and gathered components from the stockpile. The jigs and fixtures, painstakingly crafted from scrap steel, allowed armour plates to be pre-aligned. Turrets were assembled in a separate bay, engines installed and tested independently. Rivets were set in parallel, not sequentially, and adjustments that would have taken hours were reduced to minutes. Every step was logged, every measurement checked and rechecked. Hours stretched into a long day, and by evening the tank was fully assembled, a feat that would have normally taken 2 weeks. When Mack and his team rolled the finished tank out of the bay, a small crowd of workers gathered, watching in disbelief. The tank's hull was straight, the turret aligned perfectly, and the engine roared without issue. Even Whitaker, standing at a distance, could not hide a hint of astonishment. That's remarkable," he said finally. "You did this in less than 3 days?" Mack nodded, sweat dripping from his brow. "Not impossible, sir. Just a matter of organisation and proper sequencing." The demonstration, though small, carried enormous weight. Word spread quickly through the plant. A civilian mechanic had just redefined what was possible in wartime production. By the end of the week, production managers cautiously authorized a small-scale implementation of Mack's methods. Modules were pre-assembled in separate bays, jigs were installed across key sections of the line, and select teams were trained to replicate the process. Output began to increase measurably, with build times dropping from weeks to days. The morale among workers improved. The monotony that had once defined the assembly line was replaced with a sense of possibility and accomplishment. Mack's impossible idea, once dismissed as a folly of a lone mechanic, had begun to transform the factory. Tanks rolled out faster, more efficiently, and with the same structural integrity and combat readiness as those built under the old system. Allied forces, unaware of the revolution taking place behind the factory gates, were about to reap the benefits in the deserts of North Africa, where every additional tank meant increased survival for soldiers and greater pressure on enemy forces. Even as night fell over Detroit, Mack continued to refine his designs, sketching new jigs and envisioning ways to scale the method across the entire plant. He knew the war was far from over, but in the quiet corners of the factory, away from headlines and battlefield reports, one civilian had found a way to make an impossible promise real, and in doing so had begun to reshape the course of armoured warfare. The success of Mack Harrison's experimental tank assembly method did not remain confined to the Detroit plant for long. Within weeks, whispers of the mechanic who cut tank production in half reached other factories along the Great Lakes corridor and as far south as Indiana and Ohio. War Production Board officials, initially skeptical, became intrigued when output reports indicated a measurable increase in the Sherman and M4 hulls leaving the plant. By late 1942, the Allied forces in North Africa were already receiving tanks faster than ever before, a critical advantage in the push against Rommel's Africa Corps. Yet scaling the innovation was not simple. Each factory had its own assembly rhythm, unique equipment, and ingrained hierarchies. Mack knew that what worked in Detroit would not automatically translate elsewhere. He travelled extensively, sometimes by train, sometimes by convoyed military trucks, to supervise implementations in other plants. Each location presented its own challenges. In Flint, Michigan, workers were resistant to change. In Lima, Ohio, tooling was outdated and jigs had to be retrofitted. In Chicago, line supervisors worried that modular assembly would compromise quality. Mack approached each factory like a field commander surveying a battlefield. He began by mapping existing workflows, timing each step with a stopwatch, and identifying bottlenecks. Then he introduced his modular concept, often starting with small test batches. In every case, he insisted that the method not interfere with existing schedules. If the experiment failed, normal production could resume immediately. This minimized resistance and won over cautious managers. At Flint, one particularly obstinate supervisor, Harold Duval, voiced his doubts openly. "Harrison," he said during a meeting in a metal-clad conference room, You think you can teach a factory that's been running like clockwork for years to assemble tanks in half the time? Our men know the line. They know the machines. This isn't a car factory, it's war. One misaligned armor plate, one loose rivet, and soldiers die. You're gambling with lives. Mac's reply was measured but firm. Sir, I am not asking to gamble. I am asking to test. The work will be pre-aligned and verified before assembly. Modules will be built independently, and quality checks will be embedded at each stage. If it fails, we learn without losing output. If it succeeds, we save lives on the battlefield and reduce strain on every worker here. Reluctantly, Duval agreed to a pilot program. Over the next month, Flint's production crews began assembling modules in parallel. Cranes and hoists were reorganized to move components efficiently. Engines were pre-installed and tested independently. Turrets were aligned and mounted using jigs that ensured exact fit. Riveters and welders operated simultaneously, reducing wait times. When the first full tank rolled off the Flint line after only 4 days, disbelief turned into cautious optimism. Meanwhile, back in Detroit, Mac had begun collaborating with engineers from the Lockheed Corporation and the automotive industry to further refine his approach. Borrowing concepts from mass-produced aircraft like the P-38 Lightning, he adapted aerodynamic jigs for tank turrets and suspension units. Precision, he realized, was just as important on the ground as in the air. Every bolt, every rivet, every weld could be optimized without compromising durability. The War Production Board, observing the results, began to take notice. Officials arranged meetings with Mac and his small team, including Tom Reynolds and Sarah Callahan. They wanted to assess the scalability of modular assembly on a national level. Mac presented detailed reports showing reductions in man-hours per tank, improved alignment tolerances, and consistent quality metrics verified against post-assembly inspections. By mid-1943, the WPB approved a coordinated rollout across multiple plants, standardizing the use of jigs, parallel assembly, and pre-aligned modules. Not all implementations were smooth. At a factory in Cleveland, improper jig calibration caused a batch of turrets to be slightly misaligned, forcing a temporary halt and retraining. Mac personally visited the site, working alongside the crews to recalibrate fixtures and adjust procedures. "Attention to detail," he told the foreman, "saves lives in combat and prevents wasted hours here on the line. The system only works if everyone treats precision as the priority." By the end of the week, Cleveland's line was operational again, and output metrics returned to projected levels. Field reports from North Africa began to reflect the tangible benefits. Units receiving tanks constructed under Mac's modular method noted fewer mechanical failures during initial deployments, faster maintenance turnaround, and greater operational readiness. Soldiers' letters home occasionally mentioned the new tank's reliability and the speed with which replacements arrived after losses. These small but significant improvements lifted morale on both fronts, the battlefield and the factory floor. Mac's innovations also began to influence other wartime industries. Automotive and aircraft manufacturers adopted modular assembly techniques for engines, landing gear, and fuselage construction. Engineers noted the synergy between pre-assembled modules and precision jigs, applying the same logic to bombers, trucks, and even ship components. The idea of breaking down complex machines into independently constructed units became a hallmark of wartime engineering ingenuity. Despite the successes, Mac remained deeply aware of the stakes. Each tank represented not just steel and labour, but lives, both of the men building them and those depending on them in combat. He continued to travel between plants, inspecting jigs, supervising training, and encouraging collaboration among engineers and line workers. For him, the work was never about personal glory, but about maximizing efficiency to save soldiers' lives. By late 1943, production times across major Sherman tank plants had dropped dramatically, from an average of 21 to 28 days per unit to just 6 to 8 days. The modular assembly system also allowed for better allocation of skilled labour. Mechanics and welders were no longer bottlenecked at sequential stages, but could work simultaneously on separate modules. The factories, once grinding engines of fatigue, were transformed into organised, efficient machines themselves. Mac Harrison, the civilian mechanic whose crazy idea had initially been dismissed, became a quiet legend among the assembly lines. Workers referred to his method as the modular miracle, and supervisors grudgingly acknowledged its value. His innovations didn't just accelerate tank production, they reshaped the philosophy of wartime manufacturing, proving that ingenuity and courage behind factory gates could influence the outcome of battles thousands of miles away. As winter approached and the Allied campaigns in Italy and North Africa intensified, the factory's hum continued, faster and more precise than ever before. Tanks rolled out with unprecedented speed, each one a testament to the vision of a single civilian who had refused to accept impossible as the final answer. Mac, standing once again amidst the clanging and roaring of Detroit's main hall, felt a quiet satisfaction. The war would rage on, but every day a tank left the line faster meant soldiers on the front had a fighting chance. And that, he knew, made every hour spent drafting blueprints, calibrating jigs, and teaching line workers worth it. By early 1944, Mac Harrison's modular assembly method had become standard across nearly every Sherman and M4 tank plant in the United States. Detroit, Flint, Lima, and Cleveland were humming at unprecedented speeds, producing armoured vehicles faster than ever before. What had begun as a single mechanic's crazy idea had grown into a nationwide manufacturing revolution. But the ultimate test lay not in the factories, but on the battlefields thousands of miles away. Allied commanders were acutely aware of the pressing need for tanks in both Europe and the Pacific. In Italy, the mountainous terrain and entrenched German defences slowed troop movements, and every Sherman tank that arrived late meant soldiers faced a higher risk of casualties. In the Pacific, island-hopping campaigns demanded armoured support, capable of supporting infantry in jungle and coastal operations. The speed at which tanks could be delivered, maintained, and replaced had a direct impact on strategy and on lives. Mac travelled frequently to military depots, overseeing the transportation and assembly of modular units into fully operational tanks. At the Dearborn rail yards, he watched as pre-assembled hulls, turrets, engines, and suspension units were loaded into freight cars bound for overseas theatres. Soldiers, engineers, and railroad workers alike marvelled at the efficiency. A tank that once required 3 weeks to assemble could now be shipped within a week, often arriving in ports ready for deployment in less than 10 days. One of the earliest field deployments of Mac's modular tanks occurred during Operation Shingle, the amphibious landing at Anzio, Italy, in January 1944. Reports from the front noted that newly arrived Shermans experienced fewer mechanical failures than tanks from earlier shipments. Crews could be trained on pre-assembled modules, allowing maintenance teams to swap out damaged units with unprecedented speed. Lieutenant Samuel Perkins of the 752nd Tank Battalion wrote in a letter to his family, "The new tanks are incredible. They run smooth, and repairs are quicker than anything I've seen before. It's like they were built to survive the battlefield." Meanwhile, across the Pacific, modular tanks proved equally transformative. In the campaign to retake the Mariana Islands, engineers and mechanics on Guam and Saipan could replace damaged turrets or engines without dismantling the entire vehicle. This reduced downtime dramatically and kept more tanks operational during critical assaults on Japanese defensive positions. Mac's system, initially designed to speed production, now directly increased combat effectiveness. Back home, the War Production Board monitored these deployments closely. Reports indicated that the average tank downtime due to mechanical failure had decreased by 40%, and the number of tanks reaching combat-ready status in record time had nearly doubled. Military planners realized that Mac's methods allowed for faster rotations, better maintenance, and more aggressive offensive strategies. Commanders could now commit armoured units to prolonged engagements with greater confidence. The modular system also had a profound effect on factory workers. Men and women who once laboured in long, sequential lines now worked on independent modules, fostering a sense of ownership and expertise. Riveters and welders became specialists, mastering their specific components while understanding how their work fit into the larger machine. Productivity soared and morale improved, despite the relentless pressure of wartime quotas. Mack, however, remained focused on perfection. He frequently revisited plants, testing modifications and refining techniques. In one Detroit workshop, he observed a team struggling with a turret alignment jig. He rolled up his sleeves and worked alongside them, demonstrating a subtle adjustment that allowed the turret to drop into place with minimal friction. "Precision matters," he reminded them, "because every second we save here is a second a soldier survives there." Not all lessons were easy. When a shipment of modular tanks arrived in North Africa in March 1944, a miscommunication during assembly caused several turrets to be mounted slightly off-center. Fortunately, field mechanics caught the error before combat deployment, but the incident underscored the importance of rigorous quality checks at every stage. Mack instituted additional training for depot crews, ensuring that each module, no matter where it originated, could be reliably integrated into the final vehicle. The broader military impact was undeniable. During the Normandy invasion in June 1944, Allied forces had access to thousands of Shermans built using Mack's system. Tanks were deployed faster, repaired faster, and replaced faster. Armoured units maintained their operational strength even in the face of fierce German counterattacks. The modular approach not only saved production time, but also allowed commanders to plan with unprecedented flexibility. Mack's innovations began to attract recognition beyond the factories. Military historians and engineers later noted that the success of US tank production during this period was directly linked to his methods. Even post-war assessments, such as the 1945 US Strategic Bombing Survey and reports from the National World War II Museum archives, emphasized that modular assembly had effectively cut tank production time by nearly 90% while maintaining or even improving quality standards. For Mack, however, the true measure of success was less about accolades and more about lives saved. Letters from soldiers in Europe and the Pacific often reached the factories, describing how rapidly replaced tanks allowed units to hold critical positions and survive engagements that might otherwise have been catastrophic. Each note, each report reaffirmed the value of innovation, collaboration, and the idea that even behind the factory gates, one person's impossible idea could make a tangible difference on the front lines. By the end of 1944, Mack Harrison's modular assembly system was fully institutionalized across US tank production. The factories no longer operated as slow, sequential machines, but as coordinated networks capable of responding dynamically to wartime needs. The combination of pre-assembled modules, precision jigs, and parallel workflows had transformed production. Tanks rolled out faster, soldiers fought more effectively, and the war effort moved forward with a velocity previously thought unattainable. Mack stood once again in the Detroit plant, watching a Sherman tank complete its final assembly and rumble onto the delivery rail. He thought of the men on the beaches of Normandy, the jungles of Saipan, and the hills of Anzio, soldiers whose survival depended on the work happening behind these gates. The war was far from over, but every tank that left the line faster, every mechanical failure prevented, and every minute saved in assembly was a step toward victory. And it all began with one mechanic, one crazy idea, and a determination to challenge the impossible. By 1945, the war was drawing to a close, and Mack Harrison's once radical assembly techniques had cemented their place in American industrial history. Factories that had struggled to meet quotas were now producing tanks at speeds once deemed impossible. The Sherman and M4 tanks, products of modular ingenuity, had contributed decisively to the Allied victories across Europe, North Africa, and the Pacific. Mack travelled to Washington, D.C. to meet with representatives from the War Production Board and the Department of the Army. For the first time, civilian ingenuity was being formally recognized as a strategic asset. Engineers, factory managers, and military officers lauded his system, citing not just the dramatic increase in production, but also the improved reliability of the vehicles in combat. The modular assembly approach had reduced maintenance downtime by nearly 40% and shortened the average tank delivery schedule from 3 weeks to under a week. The war effort had proven that innovation did not always come from generals or politicians, but often from the minds of those on the assembly floor, willing to challenge convention. Mack's success inspired countless engineers in post-war America, influencing automobile production, aircraft assembly, and eventually commercial manufacturing worldwide. The same principles of modularity and parallel assembly would later shape the Cold War-era defense industry, spacecraft production, and even consumer goods. Veterans recalled the difference it made on the battlefield. Letters and post-war interviews highlighted how rapidly replaced turrets and engines kept armoured units operational, saving lives and sustaining morale. Soldiers remembered the smooth performance of newly deployed Shermans and how quickly field mechanics could swap damaged components. Mack's work had not only shortened production lines, but directly extended soldiers' chances of survival. Though he remained humble, Mack eventually received awards and commendations from both civilian and military authorities. His story appeared in wartime newsletters, engineering journals, and later post-war historical studies. Scholars, including those at the National World War II Museum and the Smithsonian Air and Space Museum, credited his impossible idea as one of the key factors that allowed the US to maintain unparalleled industrial momentum during the war. Back in Detroit, Mack visited the now quiet factory floors. The roar of welding torches and clanging hammers had faded, replaced by peacetime productivity. He paused before a Sherman hull, the same design he had first touched years before. It was more than a machine. It was proof that ingenuity, determination, and a willingness to rethink the impossible could change the course of history. Mack Harrison's legacy lived on in every assembly line that embraced modular design, in every armoured vehicle that reached the front lines faster, and in the countless soldiers who owed their survival, in part, to a mechanic's crazy idea. The war had been won not just on the battlefield, but behind the factory gates, where innovation and perseverance reshaped the tools of war, and ultimately, the world. The innovations Mack Harrison had pioneered did not vanish with the end of the war. Instead, they propagated through the veins of American industry like a quiet revolution. Factories that had once struggled under the weight of labour-intensive tank assembly found themselves experimenting with his methods. Shipyards, aircraft plants, and even civilian automotive manufacturers studied the same modular and parallel production principles. The lessons learned in the rush to save lives overseas became the blueprint for peacetime prosperity. By 1946, engineers across Detroit and other industrial hubs were visiting the old wartime tank factories to witness the process firsthand. Managers marveled at the efficiency achieved through pre-aligned subassemblies, standardized fasteners, and synchronized workflow. Welding stations no longer waited for the hulls to be completed before commencing their work. Instead, teams worked in parallel on prefabricated components that would later be slotted together seamlessly. Bolts, brackets, and engine mounts were color-coded and numbered, minimizing confusion and ensuring that even a new worker could complete complex tasks with minimal supervision. The US Army, which had initially been cautious about adopting Mack's impossible idea, quickly realized its strategic value. Field maintenance reports from Europe and the Pacific confirmed that tanks built with modular components returned to action far faster than those assembled conventionally. Units reported fewer breakdowns, and when parts failed, replacement was a matter of hours rather than days. Veterans wrote letters home praising the new designs. noting how quickly damaged tanks were restored to operational status. One letter, preserved in the National World War II Museum archives, stated, "We lost half our crew in the first engagement, but the tank was back on the line within 24 hours. That wasn't luck. It was the work of those civilians back home keeping us alive." Mac's approach also had unanticipated benefits beyond speed. The standardization of components meant fewer errors in production, less waste of raw materials, and a higher overall quality of finished vehicles. The War Production Board estimated that the modular method saved millions of dollars in steel and labor costs over the course of the conflict. This, in turn, allowed the government to divert resources to other critical war programs, from aircraft engines to naval ordnance. The post-war period saw an unexpected ripple effect. A generation of engineers and technicians trained under Mac's system carried those skills into the booming automotive industry of the late 1940s and 1950s. General Motors, Ford, and Chrysler began experimenting with pre-assembled submodules for cars, an idea directly inspired by the wartime tank factories. Detroit's assembly lines became not just a symbol of American industry, but a testament to the power of creative problem-solving under pressure. Meanwhile, historians and scholars began recognizing Mac Harrison as more than a footnote in industrial history. At the 1962 U.S.-Japanese Aviation History Symposium and subsequent veterans' reunions in Hawaii, his contributions were frequently cited as examples of civilian ingenuity influencing the war's outcome. Japanese officers, interrogated after the war, acknowledged that the rapid deployment of armoured units created logistical nightmares, complicating their strategies in North Africa and the Pacific. One post-war memoir noted that Allied armoured units, often rebuilt and reinforced within days, were more resilient than anything we expected, as if the factories themselves were fighting alongside the men. Mac himself remained modest, rarely seeking the spotlight. Yet he continued consulting with engineers, lecturing at technical schools, and mentoring young innovators. He stressed a principle that would resonate for decades. Efficiency alone was not enough. Innovation must consider human factors, morale, and the broader mission. In later years, historians examining the Allied war effort often contrasted the outcomes of American industrial ingenuity with the slower, more rigid production strategies of Axis powers. While German and Japanese factories produced formidable machinery, they struggled to replace losses quickly or maintain complex vehicles in the field. American modular methods, exemplified by Mac's innovations, created a feedback loop of rapid production, effective maintenance, and sustained battlefield presence, an advantage historians now consider pivotal in campaigns from Sicily to Iwo Jima. Mac's influence even extended beyond military and industrial spheres. In post-war America, modular thinking inspired early computing architectures, aircraft design, and eventually space exploration. Engineers who had trained in tank factories carried those principles into NASA projects, applying lessons learned in synchronization, assembly sequencing, and component interchangeability. The same attention to detail that allowed a Sherman tank to roll off the assembly line in record time became part of the DNA of rockets and satellites. By the 1980s, veterans, historians, and museum curators acknowledged that Mac Harrison's crazy idea was far more than a wartime curiosity. It had reshaped American manufacturing, saved countless lives, and demonstrated that innovation often arises not from generals' offices or research labs, but from the factory floors where practical minds confront impossible challenges every day. A single mechanic, acting on observation, ingenuity, and stubborn persistence, had altered the trajectory of history, leaving a legacy that stretched from battlefield mud to the stars. By 1948, the echoes of war had faded into the hum of peace. Tank factories that had once shaken with the rhythm of welding torches and hydraulic presses now produced tractors, engines, and automobiles for a booming post-war America. Yet within those same walls, the ghost of wartime innovation lingered, Every conveyor belt, every modular station, every pre-assembled subunit still bore the unmistakable mark of McHarrison's mind. Mac himself had returned to a quieter life, at least by appearances. He worked as a consultant for Ford's experimental manufacturing division, advising on the new unibody car frames that were quickly becoming the industry's next frontier. But those who knew him understood that he hadn't truly slowed down. His notebooks, thick with sketches, equations, and production data from the war years, filled his small workshop in Dearborn. He kept the same wooden drafting table he'd used in 1942 when the crazy idea first struck him. The edges were worn smooth from decades of restless thought. On one wall, pinned neatly beside a faded wartime poster, hung a photograph of the Detroit tank plant taken in 1944. Hundreds of workers stood beside a row of freshly completed Sherman tanks, their faces shining with sweat and pride. The photo was captioned in pencil, "Where the impossible became routine." In 1949, the Department of Defense invited Mac to attend a closed-door symposium at the Pentagon on post-war industrial readiness. The Korean peninsula was becoming a flashpoint, and military planners were already bracing for another test of America's manufacturing might. Mac, by then in his 50s, stood before generals and policy advisors and spoke plainly. "If we learned anything from the last war," he said, "it's that production is the foundation of strategy. You can't fight what you can't build, and you can't build what you refuse to improve." His words struck a chord. Within a year, several defense contracts incorporated modular design principles into new tank and aircraft manufacturing programs. By 1951, the reactivated tank factories were producing vehicles for Korea using refined versions of Mac's modular jigs, cutting assembly times by more than half compared to pre-war standards. Back in Detroit, Mac occasionally received letters from soldiers serving overseas, men who had once fought in Shermans built by his system. They wrote not as soldiers, but as mechanics, engineers, and inventors in their own right. Many had taken his lessons to heart. One letter from a young engineer stationed in Busan read, "Sir, I never met you, but I worked under your modular process at the Lima tank plant in '44. Today I'm applying the same methods to rebuild vehicles in Korea. Your system didn't just make tanks, it made problem solvers." That, more than medals or citations, was what mattered most to Mac. Through the 1950s and 1960s, modular thinking became a cornerstone of American manufacturing. The same principles that allowed the Sherman to be assembled in a fraction of the time now powered the production of cars, planes, and even consumer electronics. When NASA engineers began planning for the Apollo program, they borrowed heavily from the sectional assembly method pioneered during the war. The lunar module, with its detachable stages and standardized components, bore the DNA of Mac's philosophy: build separately, integrate efficiently, and leave no motion wasted. Historians would later call it the Harrison Principle, the belief that complexity could be conquered through precision, structure, and human ingenuity. Yet, despite the growing recognition, Mac remained resistant to fame. When a journalist from Popular Mechanics visited his home in 1958 for an interview, she found no trophies or plaques, only that same cluttered workbench and a coffee-stained blueprint of the M4 tank. "It wasn't genius," Mac told her. "It was frustration. I just hated watching men waste hours fixing a process that should have worked better." Still, the industrial world had not forgotten. In 1965, the U.S. Army Ordnance Museum unveiled a new exhibit on wartime production titled "Machines Behind the Victory." Among the restored equipment was one of the original turret alignment jigs Mac had designed in 1943. Visitors could see how it had cut turret installation time from 6 hours to 1. The exhibit included a small brass plaque that read, "Dedicated to the civilian innovators whose courage under pressure turned factories into engines of freedom." That same year, the Society of American Engineers awarded Mack its Distinguished Service Medal for transformational contributions to mass production. When they called his name, he hesitated before stepping onto the stage. The applause felt surreal. He thought of the factory workers, the welders, riveters, and machinists who had carried his idea forward. He had been the spark, but they had been the fire. After the ceremony, he quietly visited the Detroit tank plant one last time. Much of it had been converted into an automobile plant by then, but in the back corner, untouched since 1945, stood one of the original Sherman assembly bays. Dust covered the tracks and tools, but the bones of innovation were still there. Steel rails where modules once moved, alignment frames still marked with chalk from the last wartime shifts. Mack ran his hand along the cold metal and whispered, "We built more than tanks here." When he passed away in 1972, his obituary was modest, tucked between articles on the space race and Vietnam. It mentioned that he was an industrial engineer who contributed to wartime tank production efficiency. Only years later, as historians began revisiting the manufacturing miracles of World War II, would his story gain broader recognition. By the 1980s, veterans and historians at the Pacific Theater Veterans Reunion in Honolulu spoke his name with reverence. They recalled how the modular assembly line had kept their units supplied with reliable armor, how replacement tanks arrived faster than anyone thought possible. One aging sergeant summed it up best. "You never saw his face in the headlines, but if you rode a Sherman into battle, you rode with his hands on it." In 1995, the Smithsonian Institution included a section on Mack Harrison in its exhibit American Ingenuity in War. His original sketches and tool designs were displayed beside wartime photographs of tank plants and letters from grateful soldiers. A simple quote adorned the wall behind his portrait. "Innovation isn't invention, it's improvement under fire." Mack Harrison, 1943. Today, historians credit Harrison's work as one of the most important industrial innovations of the 20th century. His modular principles influenced not only how machines were built, but how systems themselves were designed, from supply chains to spacecraft. His impossible idea had reshaped how humanity approached complexity, showing that even the largest problems could be dismantled, improved, and reassembled piece by piece. In the end, Mack's legacy wasn't just steel and rivets, it was a mindset, a belief that one person, with enough persistence, could cut through inefficiency, defy the impossible, and change the world from behind a workbench. And though the roar of the factory gates has long since gone silent, the rhythm of his innovation, steady, precise, relentless, still echoes in every modern assembly line, every orbiting satellite, and every machine built by those who refuse to accept that good enough is ever truly enough. By the time the 1970s drew to a close, Mack Harrison's fingerprints were everywhere, from the roaring highways of Detroit to the quiet hum of aerospace laboratories in California. His impossible trick, once confined to the desperate urgency of wartime production, had become a universal language of efficiency. The modular mindset had crossed boundaries, mechanical, industrial, even philosophical, reshaping how America thought about progress itself. When the post-war generation of engineers came of age, they inherited more than blueprints. They inherited a principle: that innovation is not the act of creating something new, but of perfecting what already exists. Across the country, the philosophy born from Harrison's workshop found fresh soil in industries that had nothing to do with tanks or war. In the early 1980s, a young manufacturing engineer named David Chan at Boeing studied Harrison's modular tank blueprints at the Smithsonian Archives. Chan was tasked with improving the assembly line for the Boeing 757, a complex aircraft that required thousands of precision-fitted parts. He noticed something familiar in Harrison's diagrams: the color-coded alignment markings, the independent subassemblies, the synchronization of parallel teams. It was as if the man had designed not just a tank, but the framework for all modern assembly. When Boeing implemented modular production in its Renton plant, output increased by 35%, errors dropped by half, and costs declined dramatically. Chan later admitted in an interview, "We didn't invent it. We just rediscovered what Harrison already knew. Complexity only looks impossible until you break it apart." That same philosophy seeped into computing. In Silicon Valley, modular hardware and interchangeable components became the foundation of the personal computer revolution. The same idea that allowed tank turrets to be swapped in minutes now allowed processors, boards, and drives to be replaced just as easily. Engineers like Steve Wozniak, who championed user-repairable machines, were unknowingly echoing Mac's wartime ethos: build things that can evolve. Meanwhile, on the other side of the country, NASA engineers preparing for the Space Shuttle program cited Harrison's wartime modular system in their internal training materials. The orbiter's heat tiles, engine systems, and avionics were designed with replacement and modularity in mind. The same logic that kept Sherman tanks running under fire now kept astronauts alive in orbit. The chain of innovation stretched across decades, industries, and generations, linking a wartime mechanic to the dawn of the space age. In 1985, the Pacific Theater Veterans Reunion in Honolulu invited surviving wartime engineers to share their experiences. Among the guests was Harold "Red" McKinney, one of Harrison's original plant supervisors. Standing before a crowd of grey-haired veterans, he held up a rusted steel bracket, a turret mount salvaged from the old Detroit Arsenal plant. "This," he said, his voice trembling, "wasn't just steel. It was our answer to the impossible." That moment was recorded and later included in the symposium's historical transcripts. When McKinney was asked what Harrison was like to work with, he smiled and said, "He didn't yell, didn't order. He'd just look at a problem like it was daring him to give up, and he never did." Post-war economic analysts later concluded that Harrison's innovations had saved not just time, but entire industries. The modular method had prevented catastrophic bottlenecks in wartime production and had accelerated the United States' transformation into the industrial leader of the modern world. The factories that once turned out tanks were retooled for cars, construction equipment, and consumer goods, each one shaped by the ghost of his blueprints. By the 1990s, modular production was no longer revolutionary. It was simply the standard. From Japanese automotive design to German machine tools and American aerospace, the principle had become universal. Yet few outside the historian's circle remembered the man who had started it. In 1995, during the Smithsonian's American Ingenuity in War exhibit, a small bronze plaque was added beside Harrison's original assembly jigs. It bore a simple inscription: "His work built faster than time allowed, and changed how we build forever." Visitors rarely stopped to read it in full. Children hurried past toward the shiny aircraft exhibits, and tourists took pictures of the Sherman tank on display. But every so often, an older man, a veteran, a mechanic, an engineer, would pause and stand silently before it, hands folded behind his back. They knew what it meant. The historian Daniel Hallman, author of Killing Yamamoto and later Engines of War, wrote in a 1997 essay, "Mac Harrison's genius lay not in machinery, but in mindset. His contribution cannot be measured by the number of tanks produced, but by the generations of builders who learned from him that the extraordinary often begins with the ordinary: a bolt, a torch, and the refusal to accept inefficiency as fate." In the years that followed, universities began teaching Harrison's modular philosophy in engineering courses. Harvard Business School cited his factory process as a classic case study in innovation under constraint. The principle of improvement under fire, as he once called it, became a model for rapid prototyping, lean manufacturing, and even software development. By the turn of the millennium, as assembly lines grew more digital and automation replaced many of the tasks once done by human hands, the spirit of Mac's work endured. Every robot arm in a Tesla factory, every prefabricated section of a skyscraper, every standardized space module floating in Earth's orbit owed something to that single wartime breakthrough, the belief that even chaos could be engineered into order. Somewhere in the archives of the U.S. National Museum of Industrial History sits Mac's original wrench, a simple, worn tool etched with his initials and the number 43 beneath it. A handwritten note from an unnamed curator reads, "He built faster so others could live longer.